Hello. Hello, everybody. Welcome. Just maybe give me a sign that you hear us well and always fine on the participant side so that we can start. Okay, yeah. Okay. Okay. On the table here in So, welcome to this webinar that we organized jointly together with our sister projects, Titan and Storming. My name is Galina and I'm the communication manager of ColdSpark project. We are very happy to welcome you to this webinar. I'm just sharing some few slides while people are joining. In the registration form, we asked you to fill in your sector. So I created just a word cloud showing where people joining this webinar work in. So welcome to everybody. It's a joint effort. So we are happy to welcome people from actually all over the world. A lot of people from Europe, of course, because we are European projects, but also a lot of interest from Asia and United States, Canada, and South America. Which is very, very nice. We are very happy with this. A quick look at the agenda. We will present the three projects, ColdSpark, Titan and Storming. We are all dealing with methane splitting in some or other way. We have Maximilian Kuhn from Hydrogen Europe who will set the scene. Thank you very much, Maximilian, for taking this responsibility and joining us today. And then we will have maybe the most interesting part with representatives of Michelin and Elkem, who will tell us why industry partners are interested in our projects. And we will finish with a panel discussion where we are also quite open to your questions too. During the whole webinar, we will be using Slido. I will paste the code and the QR code in the chat so that you can access it all the time. The first poll is already open. I see that people have started answering it, but we also have a Q&A session. We will answer your questions, so feel welcome to share your thoughts and questions there. Thank you very much once again for joining. And going back to the agenda, I give the floor to Maximilian, who will share the screen and tell us more about the carbon reserves for a resilient union. Thank you all.
Thank you very much. Good morning. I hope you can hear me and you can see my slides. Great.
Yes, okay. Thank you.
I'm Maximilian Kuhn. I'm working in Hydrogen Europe, especially on regulation codes and standards, but I have been also a fan of methane splitting, how we call it, for over 10 years now, I think, and I will guide you and set the scene, and I'm looking forward for the discussion. Hydrogen Europe is the largest hydrogen association in Europe, representing the whole industry from from all kinds of throughout the value chain, from producers to consumers to transport, so everybody. And we are color agnostic. What counts is the carbon footprint. Start. Just a little bit slow, sorry. Next slide. So what have we been doing? We have been using methane CH4 and generating CO2. Hydrogen Europe produced 2 reports on the role of methane splitting. One is on alternative pathways, and the other one is together with the German DVGW, the technical body on methane splitting. So what should we do? Instead of creating CO2, we should split it without CO2, generate hydrogen, carbon, heat, and carbon credits. Carbon credits is something we can discuss later on, maybe in more details. When we look at the hydrogen transportation, we see there's all kinds of options, but to be frank and honest, hydrogen transport is not an easy thing, and that's why there's a particular interest into methane splitting, because we can use existing infrastructure and decarbonize closely to the consumers. Why is that? When we look at hydrogen carriers, natural gas is among the cleanest hydrogen carriers. It only contains 1 carbon molecule, and from there, the pathway to hydrogen is not that far anymore. So when we look at the system integration, we can see we have this gasification pyrolysis process in the middle. We can use existing infrastructure. We can integrate with biogas plants. We can integrate with municipalities, waste and industrial waste, and we integrate renewable electricity. Also, I think what is very important is that when we look at the European Commission's projections until 2040, we see a large chunk of unabated emissions. And where do these unabated emissions come from? It's largely waste and agriculture. So what kind of emissions are they? CH4 emissions that can be turned negative. If we look at industrial removals, we see that the negative emissions here is not that big, but with this technology, we can immediately turn these emissions into negative emissions, something that is desperately needed. And this is also following the waste hierarchy set by the European Union. I'll skip this slide. One of the work I'm doing is that we have been working on the ISO 19870 on the methodology for calculating the carbon footprint for hydrogen pathways, including in the annex for methane pyrolysis. This standard will be finalized over the summer and published towards the end of the year. So we have been working for more than 3 years, I think, on this, and now it's almost ready to go. So if you want to discuss this, feel free to reach out to me. When we look at the benefits of turquoise hydrogen or methane splitting, we see we need less energy to split. This is because the reaction enthalpy, and because we don't need to move. Splitting water is just more energy intensive than splitting the CH4. And another benefit is also the negative emissions. I pointed out this earlier. So it's among one of the only technologies that can abate and generate negative emissions already with existing technology today. It also integrates very well with electrolysis and methanization. When we look at land use, we can see here on an example, gas production in Saudi Arabia, the largest copper mine. Here the land use is smaller than the parking lot. And then also lithium mining, we see also here the land use would be, the footprint would be much, much smaller. When we look at CO2 compared to solid carbon, also here we see a lot of benefits, and I will not go into, sorry, the GHG emission thresholds. We also see that here these technologies can already today achieve the set minimum values. Also in steel production, there has been some papers published how that can be used and how that can be benefited in the process. And I think what this seminar is largely about is also about the carbon, and we can see that the carbon can, depending on the production process and the technology used, can differentiate, but overall carbon is a very, very valuable material. It enables a lot of industry applications. It enables faster, lighter, and stronger applications. And here we also see the advantages of solid carbon or graphite, depending on the production process. As I said, we can see a lot of good qualities of this carbon, and that is very important, I think, for the resilience of Europe and the developing of new technologies. Especially when we look at the carbon footprint of graphite produced in China, and the dependency on the Chinese value chain we see here is very high for Europe. And I think this is where we need to act now to become more resilient and independent. Also, IEA predicts a fast growth for this carbon market. So I think the discussion about these carbon markets is rather obsolete, because we can find a lot of applications. Speaking about applications and historical examples, gypsum was an industrial byproduct from the steel production. Also here, a lot of people didn't have the vision or the idea where to use it. Now it's almost a scarce commodity. When I take the train from Brussels to Paris, I see these hills in the landscape. These are slag hills. Also here we have seen in the past where to use it. But I wanted to say that for the solid carbon, we see a lot of applications, especially in all kinds of renewable green technologies, from wind energy, automotive, power, semiconductors, PV, aerospace, connective fibers, energy storage, and batteries. So in all these applications, carbon is being used, and it can be used in the future. Also, when being stored, we can see here the ratio where it can be stored. So there's plenty of options and storage space available, and storing solid carbon is much more easier than CO2. When we look at the global emissions, so 20% of the global emissions come from a few processes, and these are mainly material processes. And I try to indicate with these black and white buttons where the carbon can be applied or integrated in the future. And you can see that almost 96% of all material uses can be, and these are generating 20% of the global emissions. So these can be mitigated in the future. So looking also at the European Commission agenda, so I think also with the technologies available from the 1940s to 60s, we saw gasification and other technologies. So solid carbon can enable an oil and gas-free circular economy, potentially substituting also oil imports. When we look at graphite again, now we have a more focus on resiliencies and defense. We see on the very high risk critical raw material, graphite ticks almost all the boxes in all kinds of sectors except missiles and torpedoes. When we apply solid carbon to concrete, it has very good advantages, and of course it also helps to store the carbon there for a very long time, which also then can help to generate carbon credits. Another very important part is food security. Ammonia production, hydrogen has always played a very important role, especially if we compare here the world population with and without fertilizers. And now if we look at carbon offset potentials, we see the US and Russia, they have large offset potentials, but Europe doesn't have any. And now you can connect to the slide of the 2040 scenario of the European Commission. So we desperately need these emission sinks. And here, these technologies are enablers for emission sinks and negative emissions technologies. When we look at carbon in the nature, we can see that a lot of soil aggregation, irrigation is happening. So one of the climate drivers, #1. And here, terra preta, likely used by the Incas long years ago, is still in the ground, and it shows that it is working. When we look at the two pictures from NASA below, we can see one picture of CO2 in the atmosphere and the other one with less CO2 in the atmosphere. What's the difference? one is summer and the other is winter. So we can see that the plants are uptaking a lot of CO2, more than potentially direct air capture can do. So we follow the path of nature, and we can integrate these nature emission, or the nature into our pathway by integrating biogenic methane into the production pathway. So we also see this in the RED methodology. And with this, I'm also coming to the end of my presentation. So methane pyrolysis is key for the Green Deal. It enables the circular economy action and the energy transition. And I think most importantly, it can help avoid hydrogen transport. It can help avoid CCS problems. It can help avoid depreciation of assets, and it can mitigate immediately Scope 3 emissions today. With this, the Sustainable Development Goals here, methane pyrolysis applies to 13 out of 7 SDGs. And I think this is a very success story, and we should further help to push this in the right direction and enable these technologies to come to market, because they are desperately needed, and they're big advantage of Europe technology, also manufacturing technology and engineering technology that is happening here in Europe, and where we're not depending on other regions. So it is a way to diversify and to bring integrate systems into the overall hydrogen economy. With this, I thank you very much. And Terry, I give you over the floor to you.
Thank you very much. It was very enlightening and nice to hear what you are saying here, and it's in the importance of methane splitting. It's a key here going forward. I will try to, also give a starting point in terms of SIDE, who we are, also give a flying start to Project Titan and Storming as such. My name is Terje Hauan. I'm working as CTO in company SIDE. In case you wondered, SIDE means something in Old Norse. So during the Viking era, SIDE was something magical or mystery. And at that point in time, science didn't have the same position as today. So for us being a high-tech company, so combining that Norwegian legacy of magic and mystery, and then coming into what is the science part of this is why we are called SIDE. So it's not short for anything. It's just a good name and a good marketing yippo for us as well. So if we just understand what is SIDE doing today. So yes, I will share the ColdSpark and the methane splitting part, but to understand what we are doing today, you need to understand what we've been doing before. And for many, many years, exactly 28 years, SIDE has been delivering industrial air pollutions to a lot of industries all around the world. So basically, you have an industry which is causing pollution, air pollution. We come in and we mitigate that with our technology. So what you see on the picture is what we call non-thermal plasma reactors, or cold plasma reactors, where we connect to the client's problem. We take that problem through our reactor systems, which you see on the picture, left and right, and then we send the purified product out into the atmosphere. So that's the basis. Here is another picture showing pretty much the same. So on the left-hand side, you see what we call the reactors, or non-thermal plasma or cold plasma reactors. And on the right-hand side, you see how we drive the energy. So that's the magic ingredients in our products. It's the pulse generators. In this case, you see the Modu powers. So we have been using cold plasma, non-thermal plasma for different kinds of air pollution for many, many years. And we have industrial large-scale systems, and we have them all over the world. So we have, since 1997, delivered these systems to a lot of locations, a lot of tier 1 clients all around the world as such. So we are constantly evolving as a company. So during the past years, we also moved into the marine abatement sector. So now we are using the same type of technology to take away exhaust gas, particulate matters from large engine systems. So we can do it on a marine vessels, we can do it on a land-based facility, and so on. So that's the same. But in this case, we are providing the same as the last slides. It is a wet electrostatic precipitator in this case, and it is a power system, which is then collecting what we in this case call black carbon. I want to emphasize, when you say black carbon, it's something unwanted, polluted, filled with something you don't want. If you change around from black carbon to carbon black, you have something entirely different, but it's all carbon-based materials. So to understand this, so Seid as a company, we are delivering systems today to tier 1 clients all around the world. We focus on industries struggling with odor and other types of emissions, and we come in with our technology. On the right-hand side, you see a bit about, the client bases we have, large clients like Nestlé Group, we have Wärtsilä, we have ArcelorMittal, Nippon Steel in India, and many more. And underneath, you see some of the industries we are covering. So today, what we are going from is an existing technology and existing products, and we're moving that into a new area. So just to understand, so when we talk about ColdSpark and the European Union grants, which we received in 2022, it is about using the same foundation, building ColdSpark on the shoulders of what Seid has done for many, many years. But now we are using the technology not to remove air pollutants or reduce air pollution. We are using that as a platform to create clean and decarbonized hydrogen and elemental carbon from natural gas or biogas. So as Maximilian said here, this is a smart way of doing it. It's going to be playing an important role when it comes to decarbonization. So for us, it's same technology, same components, same competency in the company, but it's a different application. So we like to call ourselves magicians. So, this is me dressed up as a Seid man, a man of mystery. And in my whole hand, I'm holding a cold plasma or non-thermal plasma, which is the building block of ColdSpark. I'll just go back again. Maximilian gave us a good overview, but I think we need to step 2 steps back and understand. So what is this technology? What is it doing? Well, basically, it's a technology, and that goes for us, and it goes for Titan and Storming and all the other 30 companies within the range of methane splitting or pyrolysis. You take biogas, biomethane, you put it into a magical box, which is in our case called ColdSpark, and you produce clean and decarbonized hydrogen. And you produce also clean and decarbonized carbon. Just emphasize again, normally when the European Union talks about carbon, they actually mean CO2. We actually mean carbon, we mean solid elemental carbon, and that's what you get. So just to make sure we are on the same page. So we all heard about green hydrogen from electrolysis. So we also heard about BREW, which is coming from steam methane reforming, or ATR. And as Maximilian mentioned here, it's using the word turquoise hydrogen or methane pyrolysis. I also want to mention that this baby has a lot of different names based on each company's implementation. I'll tell this. Just as for electrolyzers, you will have different variants of electrolyzers. You will have alkaline, you will have AM, you will have PEM, and you will have solid oxide. So the same happens for methane splitting. You have different companies using the words methane splitting. They could use also the word methane pyrolysis, methane cracking, methane plasmolysis, or turquoise hydrogen, and 6 other names. So basically, it's just a different way of using the technology. But end of the day, it is about this unique possibility of producing both clean and decarbonized hydrogen, and as well as producing a raw material, which is part of the EU's new Critical Raw Materials Act, elemental or solid carbon in various types and configurations. So that's the basis of what we're doing. Again, I want to dive into this just to make sure you understand. So I talked about, there's a lot of approaches in the market. The main leader on this segment is called Monolith Corporation in the US. It used to be a Norwegian company, but it's taken over by Americans in 2012, 2013. So that's the basis for the majority of the other approaches, which is not us. So high gas temperatures needs a catalyst, have energy losses due to indirect heating. Carrier gases involved, carbon with impurities, often because of the catalyst, and then needs to separate the catalyst from the carbon. So those methods are often called also thermocatalytic or thermal plasmas or molten metal plasma systems or inductive heating. So you have a number of them. The difference and what we're trying to achieve with SAID is based on our legacy and our background. So we have a lower gas temperature. We don't need any catalyst in the process. We only rely on energetic electrons. So, high temperature electrons, not high temperature plasma. And we have a very high carbon purity because we don't need to separate the gas from a catalyst. And we have a very, very fine tunability on the carbon morphology, what you want to do. And I think that was the reason why the European Union granted us a project together with Storming and Titan, which will share the details on what they're doing afterwards. So that's the basis for this. And one of the key drivers for this has been our legacy, our industrial experience with non-thermal plasma, industrial systems all over the world was a very important driver. What Maximilian pointed to is a very, very important element here. A lot of people talk about green hydrogen, which is basically water electrolysis. And we all need to understand one thing here, that water is very, very difficult to get to stage of hydrogen. You need to force water with a lot of electricity because of the bond energy of the molecule. When it comes to natural gas, or basically methane, which is the core component in natural gas, that is vice versa. So the bond energy in methane is very favorable. So which means you need a lot of less added energy to release the hydrogen and the carbon from the CH4 molecule. And that has a profound effect, which again, Maximilian pointed out to, that if you use, for example, in Norway, you use Norwegian natural gas and you use electricity derived from hydropower in Norway, the carbon intensity of that hydrogen will actually be lower. So again, I will repeat, so use Norwegian natural gas, Norwegian hydropower, you create hydrogen with a lower carbon intensity than to produce the same hydrogen from hydropower in Norway and water. This is fundamental physics. It's not about electrolyzers or technology, fundamental physics. So what we're trying to do, all of us working in the methane splitting or pyrolysis or cracking industry, is to turn methane in from a villain in the climate setting into a climate hero. What you see on the left-hand side now is what we do today. So we have a fossil fuel, we do a turbine, a compressor, a combustion process, and that forms CO2 in the process. And then we are forcing ourselves to do carbon capture and storage. So that's, very expensive pathway, but it's the traditional pathway. A lot of companies are saying then, well, we can do CO2 splitting afterwards to make some sense of all of the CO2. And that's, very energetic and creates a lot of low value byproducts. So what we all as industry, we are suggesting an alternative path, which is taking CH4, splitting it up to carbon, which is now a value, and the hydrogen, which is still a value, and then you have valuable products. You also avoid the formation of CO2, and you have permanently removed the CH4 from the equation as such. So what is important about this? When we started the project in long time ago, a lot of focus was around the hydrogen. And of course, clean and decarbonized hydrogen is very, very important. But what is even more important is EU policies. And now the Critical Raw Materials Act, which was recently implemented by EU, is setting a focus on the elemental carbon. Most people, most investors, most engineers I talk to, they are not aware of the potential and the value of the carbon material. And I have to admit, I did Photoshop the color here so that we don't produce any green elemental carbon, but just to make a point of it. So this is a material which is a high value. Maximilian was into it, so I will not dive into it. But one of the key areas where you see where the value of this elemental carbon in various qualities, if you add this material into thermal energy storage system, they improve immensely. So it's a lot of potential to use this carbon material in thermal energy storages. One of the key issues, you can actually have heat the system up to 2000 or 2500 degrees. It's something you cannot do when you heat up sand or salt. Other areas, which is also alluded by Maximilian, what we see more and more is the potential of adding this as a filler material to concrete and cement, and even to replace the steel rebar systems with inert carbon structures. They are lighter, stronger, cheaper, and they do not rust. Of course, the obvious one is use this carbon material inside the battery industry, which is requiring this type of material, whether it's graphene-based materials or it's hard carbon, other ones, is immense potential in these industries. And of course, you can talk about, graphene oxide membranes. It's very, very important when it comes to water purifications. What we see already in the US, there's a US company called Modern Hydrogen, which is actually now producing graphene enhanced asphalt, which shows an immensely potential of using this into the asphalt because it makes the asphalt much longer and with higher quality than conventional asphalt products. And of course, we also see this huge drive inside what we call the carbon black, which is tires. And we have a company which will explain more about this in the future. But this is also very important because today we get this carbon from either coke derived or coal derived or from refineries, which is not something we want to do for the future. And of course, the obvious one is the steel industry. So that's a huge potential in itself as a part of decarbonization, both with the carbon and with the decarbonized hydrogen. Just to understand, we don't care as a company, as technology provider, if the methane comes from biogas, fantastic. Then you have carbon negative. So just understand, so if we take the methane from a biogas facility, we will have carbon negative hydrogen and carbon negative carbon. So this is an interesting exercise in itself. But we are also working with natural gas. Actually, this is a project we are doing in Scandinavia, where we can actually access natural gas only from 600 meters on land-based equations with no fracking involved whatsoever. And these wells are producing up to 97% methane. And those are actually deemed as biogenical resources, which means, again, it will be carbon negative. A year ago, this is where we were as a company. We were producing this elemental carbon on a smaller scale. So this is an example of the fluffy, extreme fluffy carbon we have here. So it is, 4 grams per liter. So that's the nature of it. We are doing different batches and we can actually manipulate that carbon into different qualities and we can tune the system to obtain the qualities we need. So this is what we did a year ago. Now you can see some of the qualities you can get from this one. So now we just compared with, for example, the carbon from a plasma reactor, which is the left-hand side, and we took some samples from the standard of carbon black, which is the N100 quality. So you can see similarities. We did the same from other qualities to see how that compared. Plasma reactor on the left-hand side, and then the N300 quality on the right-hand side to give a flavor. So we have done extensive testing, and we'll do much more testing as we progress on the project. A lot of people asking, so where are you today? This picture is 1 year later than the production. So what you see on the picture, just to give you a heads up, this is the current stage at TRL 5. We had the EU coming here for a review in March and passed that with flying colors. Just to understand the main elements in our system, it is a pulse generator, which you know from my previous presentation. It is combined with a ColdSpark reactor system, which is in the center. Those are both modular, so which means there could be 2 cylinders, 10 cylinders, or 100 cylinders, and there could be equal amount of pulse generators. And that is separated into what you see on the left-hand side, which is the carbon separation unit, which is a cyclone and a pulsed bag filter as such. So that's the basis for this one. This system is based what we have downstairs in our own lab, and this is what we are scaling up further. And we also applied, for additional grants from the Clean Hydrogen Partnerships later this year. So I'll save the questions for the panel discussions and also for the Slidos. But that ends my presentation. So thank you for listening.
Thank you very much, Terje. I would suggest having a look at the Slido session and the questions that are already piling up. So the first poll is already active, so you can vote it even now. Yeah, things are changing, but the favorite one is a clean hydrogen product from biogas, which motivates people people's interest in methane splitting. I will leave it open for a bit more. So going to the questions, let's see who they are for. The ones we saw are the conversion theoretical values. What is the efficiency of your process, both in terms of CH4 conversion rate and energy efficiency? I believe this is for Thierry. Thierry, are you here? Hello?
Yes, back again.
Do you hear us? We just have had a question, this one. The ones we saw are the conversion theoretical values. What is the efficiency of your process? I believe this is for ColdSpark, both in terms of CH4 conversion rate and energy efficiency.
So what we're seeing here is depending on, it's all depending on what you want from types of carbon qualities. So if you want to have specific qualities versus, out of the box system, so it's ranging in our system, without any catalyst elements involved, kilowatt hours 10 to 12, 13, depending on what we want to achieve. So, and then 10 to 12 kilowatt hours per 1 kilogram of hydrogen, that's 3 kilograms of carbon. And then the second part is, of course, how do you want to, use the carbon that could add additional cost to the system. But that's, so that's the first one. The purity of the carbon, you're looking at something which is plus 95%. We haven't seen much PAH components because, understand we have a low temperature system. So the temperature in our system is provided by energetic electrons. We don't rely on what we call conventional background temperatures, microwave systems or torches or anything. We rely on providing the majority of the energy as energetic electrons, and then relying on what you call Townsend electron avalanches.
Thank you, Thierry. So maybe this one who came first because of the votes, by using RF NBO compliant power, you would generate a share of RF NBO compliant hydrogen. Have you asked this?
Assess this. The issue is this is an interesting discussion. It's an interesting discussion because, as Maximilian said here, is we are in Norway. So if we place our system in Norway, we have access to low carbon hydropower. So that's the renewable element. But if we today use biogas, that will be completely renewable, complete chain. If we use Norwegian natural gas, that will also have extreme low carbon intensity, but it's not inside the compliant, source as such, because the natural gas is not deemed as renewable. So that will be a mix of this one. And this is something you will probably see more from the European Union when it comes to new policies and changing and modifying policies. The carbon, we see both graphene mixtures and we see amorphous structures, and we see graphitic, all of these depending on the settings in the reactor system. So basically how you tune the power system. So it's based on pulse amplitudes, pulse width, pulse duration, energy in each pulses, and so on. Yes, we have a lot of TEM and SEM analysis, and we have done Raman as well. This presentation doesn't, we don't have the time for this at this point in time. More than happy to have those conversations. Operational pressures, we are looking at, less than 3 bar in the system. So in the compression side, it's included in the balance. So we haven't included that in the balance because majority of our client is not looking for fuel cell quality 350 or 700 bar. Majority of the clients we are talking to, they are happy actually with methane, which is basically combination of hydrogen and hydrogen in the same mix. So they don't, question us about the compression part. So the purity, that's depend how much energy you want to dictate to the methane, because if you include other gases into the system, they will steal. So CO2, for example, will steal energy from the methane. So that's pretty much the question you want to do. So high quality 99% methane will have a higher efficiency than to have other gases you also need to do, because CO2 will only steal away energy from the methane. Natural nitrogen in the natural gas, we are taking that away together with H2S in a pre-treatment strap. Yeah, the quality criteria for the carbon used in agriculture. We haven't spent much time on the agriculture industry because that's the lowest bidder in terms of, with the price per carbon. We're looking at higher valuation of the carbon, which means that agriculture sector is not high on our wish list for potential clients. Purity system, we have in the pre-treatment system, there is both a carbon separation, a multi-step carbon separation. There is a pressure swing absorption system and potentially also membrane system. So there is a system for gas separation in the system. The plasma technology used, we are developing what is called a high-density plasma system, which consists of a combined DC-AC. So it's pulse modulated, high voltage modulated system. So it relies on a DC and AC work together in harmony. So it's very different from most of the other one system. So the purity, I'm not discussing the purity of H2 because H2 is secondary. So we are looking more or less at the valuation of the elemental carbon. So the purity of the H2 stream is decided by industrial application. So if you want to use it for fuel cell, you will need to do 99.999, and that's not our technology. That's commercially available products which can do that. There's no C2 in the product, so because we don't have it. So it's Anonymous is asking a lot of questions, so I think I will pass Anonymous. So until Anonymous becomes a real name, I will not answer any other questions from Anonymous. There is some deposition, but it's minor, so it is not causing any large amounts of carbon to destroy the production of the system. So these are minute depositions which will remain minute over time.
Just a quick look to the poll. Now I will stop this one and launch the second question so that you can fill it in while we are going forward to the next.
May I start?
Yes, please.
Okay. Can you see my screen?
Yes, we do.
Okay.
If you go to presenter one.
Yeah, I'm trying to do so. Okay. So good morning to everyone. I'm Patricia Benito. I'm the scientific coordinator of Storming. And today I will show you what we have done and we are still doing in Storming for the simultaneous production of hydrogen and carbon nanotubes in electrified reactors. So Storming stands for the Structured and Conventional Reactor for CO2-free methane catalytic cracking. It's a sister project that is funded in the same ColdSpark and Titan. But beside this, we included another partner because of Horizon Wide Area Cold. So we included a Slovenian partner. We are finishing this August, so we are almost in the last rush. Our consortium is made by university partners, DTU, Univo in Bologna, and University of Zaragoza in Spain, several research institutes such as CSIC in Spain, VITO in Belgium, and National Institute of Chemistry, NIC in Slovenia, and some small medium companies such as Finland in UK, Clean Carp in Luxembourg, and one moment that I will put, and Hygear in the Netherlands. And then we have our dissemination and communication partner in Belgium, EIP. So just a brief overview of my talk. I will explain you why we are doing methane catalytic splitting or decomposition. What are the challenges of this technology that is known for a long time, but it has never been deployed at a large scale. I will show you how we try to solve the issues, and I will show you some experimental results that we got for our iron-based catalysts that are able to co-produce hydrogen and carbon nanotubes, and how we, once that we prepare them in powder, we transfer them to electrified reactors. I will finish showing you some storming impact and the conclusion. You have already heard about this, so it has been very well explained before. So the advantages of this methane splitting or biomethane splitting when we are using biogas is that we are able to capture the CO2 emissions because, okay, we are forming a solid instead of a gas, and because of the added value. But this added value will depend on the type of carbon. Now, it has been seen before that we can obtain carbon black, but also graphene, carbon nanotubes, and graphite. At the moment that we applied for this proposal, that was more or less the situation in the high-level TRL. So we had plasma technologies that it has been said before has the advantage of that we don't need to separate the carbon from the catalyst. And there were some catalytic processes such as Hazer and HiCamat. The advantage of using a catalyst is that the catalyst itself is able to control the nucleation and the growth of carbon. So it means that we are able to tailor the type of carbonaceous materials that we can produce. This will depend on the catalyst, but also on the reaction condition. So for instance, using carbon black, it's possible to be produced graphite, but if we move to nickel or iron or even cobalt, we can produce carbon nanotubes. So methane splitting has a lot of advantages, but it has also some drawbacks, and mainly for the catalytic part that avoided its deployment. It's because of carbon being the added value product may also provoke the deactivation of the catalytic sites. So our catalyst will stop working and the reaction will stop, and we can have the clogging of the reactor because of the generation of a solid inside a tube. Moreover, as had been said before, this reaction is less endothermic than steam methane reforming, but still to have high yields, we need to go at temperatures above 700 or 600 degrees C. So the heat transfer is a very important point. Just to remember that the steam methane reforming is a highly emitted CO2 process, but this is also related to the generation of the heat required to perform the reaction. So what we try to do, what we have been done in storming is to develop breakthrough structural catalytic reactors that are powered by renewable electricity to simultaneously produce CO2-free or CO2-negative, where we are using biogas, hydrogen, and high-quality carbon nanotubes in a continuous technology. So we started working on the type of catalyst. We choose iron. Why? Because as I showed you before, we can produce as with nickel carbon nanotubes, but it has the advantage that is less expensive and is not toxic. So we work in identifying the effect of the properties of the iron, such as iron loading, iron particle size, and promoters on tailoring the methane activation and carbon diffusion. So we, as you can see, modifying the catalyst properties, but very important, the reaction condition, the hydrogen productivity can be modified, and also the stability. But also important is that selecting the reaction conditions, such as the activation of the catalyst with methane directly or working at 700 degrees C. We can produce multi-wall carbon nanotubes with in quite small diameters. Here you have around 15 diameters, and where the carbon nanotubes grows from the base. So we have our particle anchored to the support, and the carbon nanotube grows on the top. This is very important because once that we will remove the carbon nanotube, the catalyst won't be deactivated because the metal particle remain attached, and because of the carbon nanotube is quite pure. We achieve the results by combining experimental catalytic tests with in situ and operando characterization that allow us to confirm the base growth mechanism with some TM videos in situ. But also very important it was the characterization, for instance, by XRD, that confirm us that the only active phase is iron carbide. So if we want to produce good carbon nanotubes, our active phase is only allyl carbide and not iron metallic. For moving from the laboratory to the TRL5 reactor, we have been using also multi-scale modeling, starting from atomistic modelings by DFT and molecular dynamics that confirm us that iron carbide is the best active phase. We perform some kinetics and microkinetics, and to finish in computational fluid dynamics that allow us to improve the geometry of the catalyst. What is this geometry? The results I showed you before are performed with powder catalyst, with pellets, but our aim was to achieve structured materials. These 3D materials that have been has had an advanced design, an easy production, and a high adaptation, because we are combining additive manufacturing and guided by computational fluid dynamics. Our aim was to modify or combine geometry and composition to control the heating. Then I will show you all of these heatings, decrease the pressure drop. So we are able to keep the pressure low even we are producing carbon. Increase the heat and mass transfer, important for the heat for this endothermic reaction, the mechanical stability, and finally the activity. Here I show you some results where you can see a monolith that it has been 3D printed. And this is a CM image. And the activity as before depends on the reaction condition, in this case the temperature, but the most important outcome is that we can increase by 3 times the stability of the catalyst because of the decrease of the pressure drop. Everything without decreasing the quality of the carbon nanotubes, because our carbon nanotubes are mainly base growth and with very thin diameters. How we tackle with the heat transfer, we are using electrified reactors, and in particular, we propose 3 complementary structured catalytic reactors that can be powered by renewable energy. So we have 2 different reactor configuration, one fixed bed heated by Joule heating, and 2 fluidized bed with microwaves and induction. As you maybe know, every type of heating is based in a different phenomena. So we need a resistive material to generate the heat in the Joule heating by passing a current. We need dielectric materials in the microwave heating, and ferromagnetic materials in the induction. But whatever is the type of heating, we have the advantages that we are directly heating the catalyst. So this means that we are decreasing temperature gradients and heating losses, and then at the end increases the efficiency. And one advantage of this type of heating is that they are very, very fast. For instance, if you have a look on this slide where I show you some results that we obtained with the Joule heated reactor using 3D printed structured catalyst, you can see that we can reach 700 degrees C in just less than 20 minutes, sorry, and we can keep the temperature constant for the time that we want. This heating ramp can be changed depending on the power supply. It can be shorter or longer, depending on what we want to do. We perform tests at 700 degrees C, and what we observe is that we can reach the same performances or even better with the Joule heated, and still keeping the properties of the carbon nanotubes. Similar results were obtained in the microwave heated reactor. Here you have a video of the thermocamera that is registering what is happening in the fluidized bed. So you can see the temperature can be kept around 700 degrees C during all of the tests. And in this case, what we observe is the microwave waves not only improve the heating, but also improve the activity. We are activating our catalyst during the time on stream. So what you can see is that the activation happens much faster and that the activity is increased. In this case, what we observe is that the microwave heating, besides producing multi-wall carbon nanotubes, increases the crystallinity of the materials. That it can be seen by the increase in the G-band in the Raman. The microwave heating reactor, before it was applied for a fluidized bed, but it can be also applied for a structural reactor whenever the support is able to be heated, such as in the case of this silicon carbide monolith that was coated by iron catalyst prepared by a mechanosynthesis method. Again, the temperature is quite constant, and the carbon nanotubes are still observed. Finally, we added to the original technologies of storming that were the Joule heated and the microwave heating with this, why they are called the third one, no? That is the induction heated reactor. In this case, the composition of the catalyst is not only iron, because the catalyst should be magnetic, should be ferromagnetic, so it was required to include cobalt nickel. The advantage of including cobalt nickel is that you can decrease the temperature. Indeed, you can see that the catalysts are stable, are active from 450 degrees C, and here the activity is performed until 650 degrees C. And as you can see, they are very, very stable with time on stream. Here the scale is 12 hours. The properties of the carbon depend on the temperature, so increasing the temperature, the diameter and the size of the carbon nanotubes are decreased. We are developing currently we are working in the TRL5 prototype, but in storming we also focus in all the process development. So starting from the purification and separation of the biogas to produce methane that doesn't contain H2S because it can deactivate the catalyst, and also in the purification of the hydrogen, so we can produce hydrogen for whatever application because we are using pressure swing absorption. We have performed a life cycle assessment of the methodology, starting from the lab scale processes, that it was very useful to get the best results, or also in terms of environmental issues. And we are doing so to the final prototype. We have compared our technology with a market analysis, and we have performed techno-economical analysis that indicated us that the technology is competitive with water electrolysis, and also with steam methane reforming coupled with CCS, and even with steam methane reforming. The price of the hydrogen for sure will depend on the price that we can sell our carbon nanotubes, because they can have a very high added value. What are the impacts of our technologies? That we are switching to renewable energy in comparison with steam methane reforming, conventional steam methane reforming, because it can be also done electrified. We are improving energy efficiency and selectivity. We are producing only hydrogen. I didn't tell it before, but in the outlet of the reactor, we only have methane and hydrogen. And this improved energy efficiency is due to the direct heating of the catalyst. We can accurately control the temperature and operate at temperatures that are below 800 degrees C. Using structural catalysts, we can do process intensification. That means small reactors that can operate under transient conditions that can be determined by the supply. That can be both fixed or can renewable energy or the demand requirements, as I will show you later. We are avoiding greenhouse gas emission because, okay, we don't have carbon as a gas, but a solid, and we are avoiding burners that produce also NOx. And as I told you before, we can decrease the cost in comparison with steam methane reforming plus CCS. What are the application of the hydrogen and the carbon nanotubes that we are producing? Our technology is thought to be a small, medium scale technology that can be located directly in the consumer, so we can avoid hydrogen transport cost and emissions. So our targets are the fuel cells, so the heavy transport, and the hard-to-abate industry that can be, for instance, high-temperature heat, such as in the tile, in the tile production, in the steel manufacturing, for instance, for the brightening, and the float gas in the tin bath. For sure, also in chemical companies that are devoted to the production of ammonia. What about the carbon nanotubes? We are checking the possibility to use them in batteries to replace the graphite because, okay, as it was said before, graphite is a critical raw material and mainly produced or refined in China. And the advantages of using multi-wall carbon nanotubes is that they show improved properties in terms of energy storage in comparison with graphite. But the properties, the application are not only limited to batteries, but they are materials that can improve mechanical stability of the materials by doing composite, for instance, in aerospace and defense, as it was said before. In polymers, it can be used in other electrical and electronic materials and also for medical purposes. So just to conclude, what we have worked in this storming project is to develop iron-based structured electrified reactors that are promising for the simultaneous co-production of hydrogen and carbon nanotubes. From biomethane in a sustainable manner. We have also tested natural gas, and the things don't change a lot, so the technology can be also used for natural gas. And the electrified reactors are able to achieve enhanced performance in comparison to conventional heated reactors. Last, I want to thanks to all of the consortium that did a great job, and all of you for your kind attention, and just telling that you can still stay updated on what we will do in this last month with our social media. So if you want to do.
Thank you so much, Patricia. We are having a look at the poll, the biggest barrier to mainstreaming methane splitting today. The winner is technical maturity, which is quite understandable because all of us are research projects. Although that we have good data so far, we are still in risk, let's say. So going to the Q&A, I would just ask you to be fast because we are already slightly behind the schedule, starting with the questions with more votes. Yeah.
Okay, so maybe if I can start.
I want to read them
okay.
Just to save time.
May I start or?
Yeah.
Okay,
yes,
so the methane conversion, it decreases sometimes after the time. It can be related with the catalytic activation for sure. we have a catalyst that sooner or later will deactivate. Indeed, I didn't show this result, but we are working in the regeneration. What is the maximum conversion that we can reach? Up to 70–75%, depending on the reaction condition. Always working below 800 degrees C. But what we usually give as number are the hydrogen productivity. So maybe 15 liters of hydrogen per gram of catalyst and per hour. How long the catalyst remains active, it depends. For instance, I show you some result in the induction heating that it can remain stable for 12 hours. And the deactivation, some of the tests that we have performed in the fixed bed, the deactivation is just because of we are clogging the reactor. Yeah, we have considered the regeneration of the catalyst. We are developing a method that avoid to use that allow us to be in continuous. We form only carbon nanotubes mainly, and we form base growth carbon nanotubes. In induction heating, we also form for sometimes some graphite. Okay, we have focused on carbon nanotubes, but changing also the type of catalyst, adding some promoters, we can move to graphite. In some cases, if we increase the temperature, to graphene, but okay, we want it. No, we aim that our carbon nanotubes don't contain iron, because it means that it will be teeth growth. But if they contain iron, there could be other application, not in batteries, but in other. And that's all. I think, I don't know if I replied to everything, but...
We have also some additional questions in the chat of the meeting, if you can check.
Okay, I will check it. The size of the size of the iron particle I showed you in the slide maybe is it fits quite good with the size of the carbon nanotubes. We produce mainly multi-wall carbon nanotubes, but in some cases we have observed also single-wall carbon nanotubes. The length, I don't remember exactly the value, sorry. To use it in heavy industry plants, what we are thinking is a modular technology. So this technology we are developing right now at TRL5 with one tube, but this technology can be scale it up, increasing the number of tubes. That actually is how steam reforming works, is a multitubular technology. Of the three systems, is the most energy efficiency. We are finishing to do the LCA analysis, because we need to consider a lot of parameters, so I cannot replay this. The diameter of the nanotube decreased with an increase in the temperature. This can be related by denucleation and growth. So if you favor the denucleation, you will produce smaller carbon nanotubes. And I saw that Irene just put our Storming website link. So if you want, you can know more there or write to us. So we will reply to you.
Many thanks to our Storming partners. It's quite interesting, and without delay, we should go to Titan. Nelvan, can you please share the screen? Yeah.
Yeah. Can you see my screen?
Yes.
Okay.
Just
perfect.
go to presenter mode.
Yeah.
Thank you.
Is it in presenter mode now?
No, not yet.
Ah, here it is.
Yeah, that's
okay.
No, that's the wrong window. Can you please? That is your window, and yeah, it's
is
fine
it correct now?
Yeah.
Okay.
Yeah.
Perfect.
Thank you.
So good morning, and thank you for the opportunity of presenting our Titan project, which has a lot of similarities with storming, I have seen. So we are working on the microwave catalytic reactor for methane cracking and biogas cracking as well, for the production of hydrogen. The title involves green hydrogen, but we should have said maybe more turquoise hydrogen, and solid carbon. The project coordinator is David Farusing, who could not participate today. And I will do part of the presentation, and my colleague Marilena Radoiu will do the second part. So in our project, we want to develop a microwave heated catalytic reactor in order to convert biogas into hydrogen, of course, without emissions of greenhouse gases. We want to obtain pure hydrogen with a competitive price for the European, and also to give opportunities of development for the biogas industry. The idea in the Titan project is to use our carbons in agriculture for soil amendments, and we have also a partner who is studying the possibility of using them for silicon carbide production. The targets in Titan are the direct conversion of biogas by simultaneous methane cracking and carbon dioxide dry reforming of methane. We want to obtain higher biogas conversions, and we want to apply a microwave heated reactor, because this project is in the framework of the development of electrified reactors of the European Commission. This is the argument of the project. We want to demonstrate possibly a CO2 negative emission process by converting biogas into biochar, and accelerate carbon capture in agriculture. So we have been developing a microwave heatable reactor and, of course, catalyst for methane and biogas cracking. And similarly to storming, we finally found that ion-based catalysts were the most appropriate catalyst. So we synthesize them from iron powder, which is very cheap, a thin iron powder. This catalyst must be freezable, so we have a small particle size. The iron is a good susceptor to microwave heating. And by treating this catalyst under methane at high temperature, we cover it with layers of carbon. And this carbon-coated iron, after cooling, crushing, and again treating under methane, gives a core shell catalyst, actually, which contains about 20% in weight of carbon, which is also a very good microwave susceptor, because carbon is also a very good microwave susceptor, so it adds to the property of iron. And it's even more easily fluidized than the pure iron, because its density is lower. So you can see on the images here that we have iron surrounded by carbon layers. So we have tested this catalyst for methane cracking in a fluidized-based reactor. And on this slide, we have compared conventional Joule heating and microwave heating at different temperatures, ranging from 750 to 950 degrees C. You can see that with microwave heating, we always have higher performances, both for methane conversion. We reach the thermodynamic equilibrium at 950 degrees C. And also the hydrogen production is also higher. So we think this is nothing magic with microwave heating. We think it corresponds to a more efficient and localized heating of our catalyst under microwaves. And you can find more details in the paper, which is indicated there, which has just been put online on the Elsevier website. So we can have a look. We had a look, of course, at the temperature of the catalytic bed during methane cracking. And we can see here infrared camera images of our reactor and the fluidization at different temperatures. You have a temperature scale on the right, and you can see that at any temperature applied between 750 up to 950 degrees C, we have a homogeneous temperature distribution in the catalyst bed. The fluidization is very efficient, and the interesting point is when we go back to the final temperature of 750, we see the large increase in the volume of a catalytic bed compared to the starting point, and it corresponds to the carbon storage on the catalyst. So we have looked in more detail at the nature of carbon deposits on our catalyst. So on the left, this is the same image of a fresh catalyst. We see it is covered with graphitic carbon platelets. And after the catalytic reaction, we have much more carbon added on top of this. We have indeed carbon filaments. We are not sure it is nanotubes. We think it's rather simple filaments. And also a lot of disordered carbon. So we have a high carbon storage capacity because in the spent catalyst we can have up to 74% in weight of carbon, while in the fresh catalyst it was only 20% in weight. But the issue is that in fact this carbon is not easily separated from the catalyst particle. And this is a bit of an issue that we have tried to solve. We have investigated how catalyst doping can modify the nature of carbon deposits and probably lead to easier separation. You see on the left, doping leads to much more carbon filaments, which hopefully will be easier to separate from our catalyst. And also we have tested the possible regeneration of a catalyst because if we can't remove the carbon, at least at some point we will have to regenerate the catalyst. And we can see here we performed environmental scanning electron microscopy study. And this is the catalyst at 800 degrees C under CO2. And you see on the left it is covered with carbon. And on the right, after 30 minutes of treatment, most of the carbon has been removed. So at least the catalyst can be regenerated. So I will leave now, I will let my colleague Marilena talk about the scale-up of the microwave reactor technology.
Thank you, Nolwenn. So in terms of the scaling up of this microwave reactor technology, I just wanted to remind you that we started the TRL3, and by the end of the project, which is going to be in about 16 months from now, we need to arrive at TRL5. So in order to do this scaling up from 3 to 5 TRL5, we went through two different if you want, steps. One was about the process scale up. So obviously the fluidization under microwave heating, it's a difficult scale up because the fluidization obviously depends on the gas flow, but that also depends on the temperature. It depends on how the catalyst heats inside the fluidized bed. It depends on how the catalyst absorbs the microwave power, and obviously depends on how the fluidization is done. And then in terms of how to do this, we use the fluidized bed reactor modeling. So there are the process models using hydrodynamic, heat transfer, and microwave. So that means the microwave simulation, electromagnetic field simulation. and then also the catalytic kinetic models, and using Langmuir and power law expression. So in terms of the process scale up, so this is what we are doing. Next slide, please, Nolvan. And in terms of the second step is obviously the equipment and the test bench upgrade, so the scaling up. And in order to do this, we started by performing obviously a risk analysis. We are working with gases that are highly explosive and also with potential products that could be toxic. So we've done the risk analysis using the failure mode and equipment analysis method, that helped us to decide what the main components of the TRL5 test bench would be. Next, please. Next slide. So some of these components are here. I'm not going to insist upon those, that there are at some point, working with this, all these gases. Once again, I mentioned we have to be in an ATEX zone. We also have to have all the interlocks for safety related to any potential carbon monoxide formation and leakage, microwave leakage, etc., etc. So in terms of that, I'm not going to insist, but happy to answer any questions. In terms of process control, we also, what I would like to mention is that we also look at, we do thermal imaging and we control the temperature of the reaction using temperature and microwave power. So I will go back to this later, but next slide, please, Nolvan. This is a photo of the test bench, and I will try to explain here. First of all, in all our project, we use the 915 megahertz frequency of microwaves. Most of the project that I've seen, including storming, I believe they use 2450 megahertz, which is like the conventional frequency, which is used in projects. However, 915 megahertz is very important because this is the direct industrial scalable frequency. So we started this, we are continuing with this frequency, and I will explain the test bench. It contains a solid state generator for our experiments. It's a 2.5 kilowatt microwave generator, which this testing scale, the important is the control of the energy, the precision of control of the energy. And then the microwave line, it's a standard microwave line containing impedance tuners. They are manual impedance tuners. It also contains, I don't have the mouse control, so I don't know if you see my mouse here. Sorry, so to the right-hand side, the first photo represents the microwave cavity. It's a monomode cavity, which is modeled in the middle photo here, to the right. And through this cavity, our reactor, it's a dielectric tube, which is made out of quartz at this stage, okay, within which we create a fluidized bed and within which we pass the methane, or I mentioned that we pass methane from a cylinder for the time being, or any mixture between methane and CO2 to simulate biogas. So the fluidized bed is created inside the microwave field, and here in the lower part, we can see what Nolven also showed. We can see the direction of the flow and the fluidized bed at the around 850 degrees Celsius. It's all red. We protect our quartz tube with some insulation. We want to keep the heat inside, so we want to maximize the energy efficiency of our reaction by using the insulation around the reactor. And other than that, so in terms of going back to the photo, so I showed you right in the middle is the microwave cavity, and then we analyze the inlet and outlet of our reaction with a micro gas chromatograph. And then we use, I mentioned, temperature control, and we do this through the side chimneys here, one thermometer, so infrared camera and pyrometers we use. One is going to measure but also control the reaction, so adjust the microwave heating, microwave power, in terms of the temperature automatically, so we can fix the temperature of the reaction, and then the microwaves will just be adjusted. It contains a lot of security components, as I mentioned, and electronic components. All of our test bench is inside an extracted hood, if you want. It's much bigger than that, and everything is done automatically in this. Right? So next slide, please. So here it's a video. So Nolven is going to start this. So I just wanted to put a video here showing what we see with conventional camera and infrared camera. So in terms of the fluidized bed, but also the importance of these photos is to show that the microwave energy is absorbed homogeneously by the bed itself. Okay, next, please. Would you like to finish, or shall I?
Well, as you want, I can finish because I wrote the conclusion, so maybe. So thank you, Marilena. Up to now, we started this project in September 2022, similarly to storming, but we have one more year because this is a 48 months project. So currently we are at month 33. So what we could achieve and show is that microwave heating combined with fluidized bed technology gives a very efficient reactor for methane and biogas cracking. We can heat the catalyst very rapidly at high temperature. The catalyst bed temperature is homogeneous, and we produce pure hydrogen, at least from methane. There's no hydrocarbons associated. We scaled up this reactor. We started with a lab scale reactor, and now we are working to have running the TRL5 reactor. We have also partners who I didn't have time to mention too much of their studies because they work also on life cycle assessment and techno-economical studies, and they assess the process for small and large biogas production plants. From their results up to now, they showed that it's very important to control the methane leaks, because methane is a very strong greenhouse gas, and the slightest leak can ruin the potential for carbon emission, negative carbon emission of a process. So they are really critical. From the economical point, there is a gap between the gray or green or turquoise hydrogen, a cost gap, and clearly a lack of specific and effective funding for biomethane and biohydrogen. If we plan to convert into electricity, they observe that a fuel cell is required, of course, but they considered a solid oxide fuel cell, and it constitutes the main cost of the process. It's a very high cost. So in the end, they suggested that using a combined heat and power unit would be a better option.
Thank you very much, Nolven. We are really running out of time, so
okay,
if you
I have
would
finished.
like
It's my last slide. Okay, so I will go to the the project, of course, the European Commission for funding this project, our partners, and thank you for our attention.
Thank you. It was really very interesting. Can you just answer the first question? Do you need to upgrade biogas to biomethane? And maybe the rest in the chat so that we can proceed. We are running really out of time. Do you need to upgrade the biogas?
To remove pollutants from here, if there is sulfur or other pollutants, yes. But the objective is to use directly biogas, which means also CO2. So we have been working on it, but it's different from methane splitting, just because we have CO2, and as I showed, CO2 can also gasify the carbon. So we can accept a certain amount of CO2 in methane, it works well. But as soon as the CO2 concentration increases higher to 10 or 15%, we start to have a lot of carbon gasification. So we lose carbon, solid carbon.
Thank you. If possible, please just answer the rest of the questions in the chat. A quick look to our active poll about the type of hydrogen that our participants expect that offers the best balance by 2030. It's the low carbon hydrogen. So going to Michelin, sorry for the delay, and the floor is yours, Pierre.
It's okay. Thank you very much. Can you hear me well?
Yes, always perfect. The slides are also fine.
Thank you very much. So thank you especially to ColdSpark to give me the opportunity to explain why and how this methane splitting, methane cracking, whatever you call it, technology has an interest for Michelin and I think for the tire industry more globally. Let me check. Yes, at Michelin we have a global, worldwide organization for R&D, and just want to show you here that we are usually talking about three main timing horizons: the advanced research, the pre-development, and the development. I belong to the advanced research team, so developing new technologies for 5, 10, 15 years from now. We are looking for new technologies that will enhance the performance of our tires. I will explain it a bit more in this presentation. And the advanced research is mostly driven here in Clermont-Ferrand, so center of France. Michelin is well known for its 130 years of innovations, and I just want to highlight the two last ones, Totem and Demos tires, that are tires containing a high renewable or recycled content of materials. That's one of the key and of the main focus on my side, on the R&D here, to develop new materials that will in the end increase the renewable and the recycled content of our tires while maintaining or even enhancing the performance of the products. And here we have a target, a very short-term target now in 2030, to reach 40% of renewable and recycled materials. Today, I believe we are at 31%. The 2030 milestone at 40% is only a milestone. The final goal is 2050, where 100% of our materials will be sustainable or recycled. So that's the main target. And we are working in advanced research to develop and boost those technologies on the market and make them available to the community. The recycled and renewable target is very important, and we have clear goals, but that's nothing without CO2 reduction goals also. And here we want to reduce the scope 3, especially related to raw materials purchasing. So here today we are talking about carbon black. So we want to reduce the CO2 emissions coming from the purchase of those materials. And we have also a strong objectives of reductions, about 30% reductions compared to 2019. So you understand that we will at some point need to switch from relatively CO2 intensive products to low CO2 intensive technologies. Here, I just want to give a few examples of renewable and recycled and come back about the definitions that Michelin is using. A sustainable material is either renewable, which means that you can renew the feedstock within the lifetime of a human being. So let's say 80, 100 years. That's the renewable part, and recycled means recycled, obviously. We are not also targeting only renewable or recycled material, but we are always looking at the life cycle assessment of the products we are developing. And the life cycle assessment for tire applications, a huge part, about 80%, it depends on the tires you're talking about, 80% depends on the use phase of the tire. So when you have it on your car, on your truck, on the road. So the impact here will be the performance. If you reduce the wear performance, the rolling resistance performance of a tire, you will totally destroy the life cycle analysis and degrade it. So it's not acceptable. That's why we are looking at renewable, recycled material with at least the same performance. And because of our DNA of innovations and because of the request of our clients and customers also, we want to look and we want to develop also fillers that will enhance the performance in the end. We are not doing it only by ourselves. We are doing it with other companies. We are doing it with startups, with well-established companies, and we also used to work in European projects such as Black Cycle. That was a key helper to develop the sustainable carbon black, so carbon black produced from tire pyrolysis oil, and recovered carbon black also, that is one key reinforcing fillers that will bring sustainability and circularity to our tires. So we are not doing it alone, we are doing it with many different people, companies, projects, and that's the core of our open innovation strategy. So why am I here today? I'm here today because we are talking about carbon product that is black and that may look like a carbon black. So I just want to give you a few insights about what is a carbon black and why it's important to the tires. A carbon black, you will see, and you will, I hope, learn it during this presentation, is a highly engineered product that is about 25% of the weight of a tire. So it's a huge part of the tire for sure. Reinforcing fillers, today we have mostly two main families, precipitated silica and carbon black. So carbon black remains the big volumes, the bigger one. For both precipitated silica and carbon black, you have multiple grades that answer specific norms. I will explain it. And we call it reinforcing fillers. Reinforcing means a lot of things, in fact. When you add a filler, a reinforcing filler to rubber, natural rubber, SBR, BR, whatever rubber you're talking about, you are totally changing the tear properties, the rigidity, the traction performance, the fatigue resistance, for example. So all of those properties are what we call reinforcing properties and are key to the final tire performances. So carbon black specifically, it's a highly engineered product. Again, it's not just small carbon dots. It's much more than this. And it's well defined by the ASTM D1765 that defines what are the key characteristics of carbon black. Multiple grades, again, are available. In the ASTM norm, you have more than 40 grades, I believe. In a tire, you usually have more than 10 different grades. Ranging from 10 to 150 square meter per gram. You can have also a few higher surface area grades that exist. And you use it, and there are multiple grades because there are multiple tire posts and tire usage. So you don't need the same properties, the same reinforcing properties on the sidewall of the tire or on the tread of the tire or on the inner liner. So each of those different parts of the tires requests usually a specific grade. Carbon black is a key product for the tire industry. And just to give you one number here, it's about 75% of the carbon black worldwide production goes into the tire. The rest is whatever is black around you should at some point contain some carbon black. And here I have a quick schematic about the structure and fineness. It's usually the key parameters that define the carbon black grades. And all the STM grades more or less falls into this dashed area here of structure and fineness. What we are looking for today with this technology, and we believe that methane splitting can hopefully produce carbon black at some point, and that will be useful to our tire industry. So what we are looking for is mostly what we call hard grades or reinforcing grades. That's usually defined as the N300, N200, or even N100 series. So we are talking about carbon black that have at least 80 square meter per gram, and the structure may vary also. Why we are looking specifically for those grades is because this is the highest volumes in our industry. So if you want to make a strong change and a strong impact, you need to develop that kind of reinforcing grades. And also because we believe today we have multiple, never enough, but multiple options, sustainable options for what we call coarse grades. So the 500, 600, 700 series, so coarse carbon black. We believe we have technologies here that will answer our needs in the future. And we now want to focus on more on other grades. You've maybe heard about sustainable carbon black from Black Cycle, so a former European project. Sustainable carbon black can answer those needs, but still we need other technologies that will also bring volumes that we need, the volumes that we need. Oops, sorry. So why plasma technology? Plasma technology to us, we would like to see it as a new way to produce carbon black, because carbon black, as you may know, is today produced by the furnace process. So it's a partial combustion of fossil feedstock. And when you are talking about partial combustion, you are talking about CO2 emissions in the end. And we believe the plasma technology can make a difference here. First, to reduce the impact because of the high yield, usually of plasma pyrolysis technologies, and the low CO2 emissions associated to this high lead of feedstock conversion. And why methane here? Because methane we could transfer it to sustainable and renewable resources if you use biomethane, biogas, or I think there's you talked about landfill gas, wastewater gas. There are multiple sources of renewable gas, and that will be key also for us to meet our sustainable objectives in after 2030 probably, because we see this technology as relatively long-term technology, long-term development technology. So the major challenges for the methane splitting technology is first to meet the carbon black quality standards. Carbon black, again, I just want to be very clear, it's a highly engineered product. It's in the STM, you define maybe 80% of what is a carbon black grade, and then 20% remains either unknown or not so well understood. So carbon black grade and developing carbon black grades is really a tough job, but we believe that with this technology, we could meet our requirements. Again, we need, at Michelin at least, we need reinforcing grades, so over 80 square meter per gram. If you have low reinforcing grades, it may be interesting also, but the market and the impact you will have on our industry will be smaller. And in the end, we need a technology that will be able to scale up and to be at scale, so multiple KT per year. That's usually the size of production sites for carbon black. It's more than 50 KT per year on one site. So that's important to us also to have very large production capacities. And in the end, the reinforcing properties of the carbon black you will hopefully produce will be key, really, and that will be the starting point. If we can have reinforcing grades, then we need a way to develop it and to go at scale and to have a strong impact on our industry. Thank you very much.
Thank you so much, Pierre. This dialogue between us as project partners and industry is really very helpful and deserves a lot of attention because it's the actual application of our work. So a quick look to our active polls. Yes, our participants say that low carbon hydrogen from methane splitting should qualify under the EU's renewable or low carbon hydrogen framework. So I'm launching the next poll, and on the other side, at the same time, please Elkem, it's time for the Elkem's presentation. So I would invite Christian.
Yeah. So I believe my presentation should be okay now.
Yes.
Yes.
Yeah. So thank you for the opportunity to speak and be a part of this webinar. So my name is Christian Stangeland. I'm an R&D engineer at Elkem Technology. So today I'm going to try to share our view on the potential application of methane splitting in terms of our current operation and also an innovative approach that we are developing for producing silicon. So first, silicon has been defined by the EU as a strategic and important critical raw material. So there's a few reasons for this. It has a very high economic importance, as it's, for instance, as a semiconductor, it's crucial for electronics, AI development, and building of digital infrastructure. It also plays an important role in terms of the renewable sector for solar cells and wind turbines, and as an alloy and agent in aluminum products. So right now, the world silicon production is almost 80% of it is produced in China. So they have expanded significantly over the last decade. In terms of the EU, they import around 40% of its silicon from Norway, which is only responsible for around 5%. So a significant part of the silicon in Europe is imported from China, which poses a supply risk. So it would be ideal if a larger fraction of the silicon could be produced within the EU. So I'll try to give a brief introduction to the silicon production process and specifically about the role of carbon. So on the right here, we have an illustration of the silicon furnace. So the materials that go in is the quartz, which is the source of the silicon. And then we also have a mixture of different carbon materials, typically coal, coke, or charcoal, along with some wood chips. So the role of the carbon is basically only to remove the oxygen from the silicon. And it's not really feasible to replace carbon with hydrogen to do this chemical reaction. So we are very reliant on the carbon material. So today this is in the form of larger lumps, we call them, of coal and so on. And we expect the material properties from pyrolysis or plasma methane splitting to be more of a powder. But that's okay. We are developing the technology and the method to take this powder and turn it into something that we can use in the furnace. So the direct emissions roughly around 5 kilos per kilogram of SI in terms of the CO2 emissions. One last thing, on the top we need to burn a lot of these gases that come out. So in the current materials there's a lot of volatiles and so on, and all of this has to be burned, and then eventually it's all released as CO2 out of the process. So we have a few different pathways for reducing our CO2 emission. One of them would be to go for biocarbon materials. And there we have an issue, or we foresee that the issue is the availability and also the cost. It's a lot of competition for the bioresources. Another option is to continue using the current materials like coal and so on, and then combine it with CCS. But the problem there might be that when the producers of electricity, steel, and so on move away from coal, the small fraction that is coming to us might become very expensive and might not even be produced anymore. So then we need a new source of the carbon material. And that's where this methane splitting comes in. So Elkem Zicalo is a concept where we start off with our silicon production here, and we capture the carbon oxides. And in the first step, we need some external hydrogen to do a methanation, to make it into something that is more easily to convert back into carbon. So the methane splitting would be then the step where we convert our oxides back to the carbon raw materials that we put in the furnace. And then we have an agglomeration step, which is where we make the carbon powder into something that we can use on our furnace. So in the Zicalo concept, we are sort of developing the two bottom boxes here, while we rely on external technologies or providers for the top, for the methanation and the methane pyrolysis. So this project we also received a Horizon Europe project last year, where we are trying to look at this concept both for the production of silicon, but also manganese, which is another metal that is quite hard to do anything about, only using hydrogen. So the other option then would be to continue along the CCS route, but then we need to look at somewhere to get our carbon materials from. So in that case, natural gas might be a suitable carbon supply if we have methane splitting. So in Norway, most of these metal producing locations is around the coast. We have access to natural gas within Norway, so it should be okay. So if we currently use around 1.5 million metric tons in this industry today, we would need around 2 million tons of natural gas. And that would only correspond to around 5 days of the Norwegian gas export. So it's not a huge amount. At the same time, we would co-produce around 500,000 tons of hydrogen. And the main thing we expect is that we have significant energy savings. So we think that you would end up around 15 to 20 terawatt hours for the production of this amount of hydrogen if you use methane splitting instead. So in this scenario, I guess the methane splitting would be like an external company that provides us a carbon material that we then take into our process. And we could also reach carbon neutrality using this approach if we combine it with the CCS, but the initial just replacing coal or the current materials with something from methane splitting would already reduce our emissions by about 30%. So overall, then we have two scenarios that we foresee that methane splitting could be a part of our process. So one of them would be, as I mentioned, as the external carbon supplier. The other one would be that there are part as a technology provider in developing this concept. So we don't really have any very strict carbon requirements in terms of, carbon black or the structure and these things. But it's very important that there are very low levels of impurities. So in terms of iron or nickel or most of the other types of metals, it's very strict requirements. Some exceptions maybe to aluminum and calcium that we could theoretically refine out. It would be okay if the carbon was easy to handle in the agglomeration step, but I think most carbon black that is produced today, they have some kind of process to make it into something that we are able to use. So we already have some qualification programs for taking different carbon blacks, taking it into agglomeration step, and then seeing how it does in the process. When it comes to the cost level, right now, the price that we pay would be around maybe 180 per metric ton of fixed carbon. So ideally, the methane splitting carbon would be similar to this level, but that might depend, on if you start having CO2 taxes and a few of the other things that might be implemented, it could be a little bit higher. But so I think compared to what the carbon nanotubes and the carbon blacks that we saw earlier, the price is probably a lot lower. So we might be more looking at those that are focusing, on the hydrogen production rather than what the carbon is. So I guess I tried to finish a little bit quicker since we were so far ahead of time. I think I've covered the key parts. So I don't know if there's any questions, maybe from the chat.
Thank you so much, Christian. We go ahead. I'm just sharing a word cloud we are creating together about the opportunities for carbon valorization. And we go to our panel discussion. I give the floor to Michael Kuttner from IPBK. Michael, are you there?
Yes. Hello. Good afternoon from my side. Yes, so we are now have reached the panel discussion in our webinar. And to set the tone, it is important to say that yeah, we still need support for our systems. We also need support if we want to produce the hydrogen and the solid carbon from biomethane and from biogas. And at the moment, at least in Germany, biogas and biomethane plants are struggling. They are looking for other income. And we are biogas, participating from the side of biogas in ColdSpark. And we seeing that problem that additional income is badly needed. And I think ColdSpark could be and methane splitting and using hydrogen and solid carbon could be another income stream, but it needs to be developed. So I have a question to all speakers, and it's please go on a 30-second pitch. Why should biomethane splitting get preferred research and development infrastructure or subsidy priority from, for instance, EU policymakers or national policymakers? So could everybody set a 30-second pitch on that topic?
Just a note that our next poll is launched, so you can use the moment to answer it too. So.
Shall we start in an order, or?
You can start, Marilena, since you're already there.
I can start. My pitch would be referring to the microwave sort of application, like in the project Titan. I believe in terms of scaling up the technology, having a microwave reactor close to a biomethane plant would be important in terms of scale, but also in terms of producing the hydrogen for being reused perhaps by the biogas producer for their own needs, and the carbon could be used exactly at the point of producing it.
Well, I'll go ahead. I think it's important that the policy documents is including methane splitting, no matter whether it's biogas or natural gas, based on the carbon intensity. So if you can produce something with a lower carbon intensity than what you do with elemental carbon or solid carbon or hydrogen today than you can with green or other alternatives, you should follow the laws of physics and provide, not necessarily subsidies, but the same rules. So there is the key point here. So we should follow, numbers, not colors, when it comes to what is logical for moving forward. And of course, using biomethane as a starting point will lead to carbon negative hydrogen and carbon negative carbon. So that would be advantageous in any case. So it's a logical move to do. Thank you.
Any other pitches from the speakers?
I've just maybe a word on my side. I see this technology as key to produce in Europe the products that winning, being carbon black or graphites or nanotubes. So it's a great opportunity for low CO2 emissions and low CO2 intensive technologies to produce materials that will be key for new technologies, being automotive, tires, whatever.
Yeah, I think also I don't know the natural gas, biomethane, I think both are important, but I think it allows, you can start to look at new hydrogen applications, new carbon applications, and so on. That, yeah, especially if you have to wait for green hydrogen, it will take a very long time, probably decades before you have enough to start developing the industry. So I think it allows the industry to start to develop much quicker than it would only using green.
Yeah, and using biogas for places where there are not natural gases will be nice. No, we don't need export, so we are producing both hydrogen and the carbon materials just made in Europe and decreasing greenhouse emission. There are a lot of places where biogas plants are currently running, and it's expected to increase the production of biogas. So it could be good to feed methane pyrolysis or methane splitting.
What I also want to add is that biogas or biomethane plants are decentralized plants, and I hear from Pierre Laurent from Michelin and others, they want to have huge amount of carbon black in one spot. So how does that combine with your needs if we have decentralized biogas plants? Of course, we can all pipe the biomethane or put it into a pipeline, but in the case of Titan, for instance, they use pure biogas, so we don't have yet raw gas pipelines which are really centralized. So how does that combine with your needs?
Yeah, thank you, Michel, for the question. That's indeed a key aspect. And at the beginning, when we looked at those decentralized production of hydrogen, I was a bit worried because there was no chance to meet our big volumes. But in fact, when you look at the needs, if you want to decarbonize steel industry or huge industries like this, it's decentralized, yes, but still the needs are huge on one side. So when you produce 1 kg of H2, you produce 3 kg of carbon. So in fact, in the end, we think that the decentralized model may be also a good model to us. Because
okay, so yeah, and if you need it more centralized, you can take biomethane out of the grid. I mean, now we have the possibility to even trade biomethane over borders or.
You have been frozen, yes, but then you are asking the question.
Biomethane.
Yeah, but then you have the question of certificates, mass allocation, that kind of stuff.
Of course. Yes, of course. Yeah.
Endless discussion.
Yeah. Yeah. Okay, so I think the round is concluded for this first question to all speakers. Now I have a question for the Titan project. So microwave-assisted pyrolysis of biogas is pioneering. What are the greatest technical barriers of scalability risks to commercial development? What are your highest risks for commercial development and deployment?
I'll probably start in terms of the microwave technology itself. So one of the challenges is going to very big scales. So a microwave generator at 915 megahertz today, it's available up to about 125 kilowatt. So if we are talking about megawatt scale, then there are two possibilities, either using the same frequency and having modular structures or multiple free dice bed reactors, each of them about 125 kilowatt. Or another possibility is there is another frequency which is available for industrial application, which is a bit lower. It's about half, 433 megahertz. We can also go to this frequency because it's not a plasma-related process, it's only a heating process, this frequency would also work quite well. The advantage of this frequency is that if the industry obviously it's interested, this frequency, a magnetron can go up to anywhere between 500 kilowatt and 1 megawatt. So it will be a lot easier to achieve the industrial scale in this process. So that's in terms of microwaves. Another challenge is today, the microwave technology is not well understood by the industry. So I believe that's a very good challenge to resolve, to educate the industry what exactly microwaves mean, because we are also, the knowledge sometimes is related to the kitchen microwave oven, and there is a very big gap between that oven and the industrial scale. So my message is that we need to educate the industry, that the microwave technology, it's an electrified sort of heating, but it's more than that. Microwaves will be only absorbed by the product needed to absorb this energy, and therefore, if everything is well built, we can expect energy efficiency, and I always talk about energy efficiency, which is higher than any other electrified processes. And again, I will go to. We mentioned quite a lot of renewable energy, microwave generators, they can work with renewable energy as long as the grid is done as such as the power is stable, because like SAID's or ColdSpark's technologies, microwave generator, they also use high voltage lines, they convert AC to DC, so they need high voltage lines. So at that point, renewable energy is always possible, but renewable energy doesn't mean you put a microwave generator connected to solar panels or wind turbine. So it comes from the grid or from a nuclear plant. It comes from the grid, and I believe in Europe we also need, in terms of this very high demand of electrical power, we need to work towards those grids that are stable, whatever smart grids, whatever we call them today, that integrate all this renewable energy without huge fluctuations. So for the industry and microwave technology, I believe these are the challenges. I will probably let Nolven talk about catalysts.
Yes, I wanted to add some words about the catalysis part and the microwave, because we had no experience in this when we started the Titan project, and it happened to we quickly understood that it was very complex from the catalysis part, because it's really complex physics. It's completely different from the way we heat our catalysts traditionally in catalysis. And we had to adapt. We had to learn a lot of things about physics. Not any catalyst can be heated by microwave, so you have to find the appropriate catalyst composition. And it also requires some really important research from the catalytic process part.
Thank you very much for your elaborate answers. We go to the next topic. I would address Elkem, Christian Stangeland, and ask, integrating methane splitting into your silicon operations, how do you ensure the hydrogen and carbon byproducts are meeting the quality and the volume needs of your smelters, of your furnaces?
Yeah, so it depends, I guess, if it's as a carbon supplier or integrated, but here it said integrated. So in that case, we have some external hydrogen that needs to come in from outside, in addition to the hydrogen we generate inside the process. So all of those requirements for the gas stuff is related to the methanation part, the methanation catalyst, and also some of it, of course, to the methane splitting process itself. But at least we don't need any fuel cell quality of hydrogen, so it's much lower requirements than fuel cells. For the carbon, the qualification for carbon, we can start today to qualify a carbon material from a methane splitting process. Eventually, we will build a larger demonstration pilot with some type of technology if we go forward, with the Michelin concept to higher TRL 7 or 8 and so on. So then we could qualify, the technology there as an integrated part of our silicon production process. That's some years in the future.
Okay, thank you very much.
Yeah.
So my next question would be for Michelin, Pierre-Laurent. Methane-derived carbon for reinforcing fillers. How does this compare to your current carbon black supply in terms of performance and supply chain security?
Today, in terms of performance, I can't answer, and I don't really know, in fact, because we at this point we hope the technology to develop and to meet the carbon black standards and quality. What we need is carbon reinforcing grades of carbon black, and that have also, it's a key aspect I'm repeating every day, that are stable in terms of quality. And at Michelin, we are very strong and very strong quality standards, and the stability of the product is a key aspect. We don't know today if producing high volumes from biomethane or methane will help this stability. Maybe because if you compare the stability and the quality of this feedstock, the composition, compared to the one that are used today to produce carbon black, we may think it will be helpful, but it needs to be demonstrated.
Okay, thank you very much. And then we also want to ask the ColdSpark project. I think that's Terje. The pulse-powered methane splitting delivers clean and pure carbon. How are you developing the markets or the partnerships to ensure that carbon becomes a valuable material and not a waste? I mean, if we calculate all the methane being split into carbon and hydrogen, it will be a huge pile of carbon. What to do with it?
Well, it's a good question, and I think the majority of our discussions is the combination of clients looking to use hydrogen, low carbon hydrogen, together with elemental carbon, and to use that in existing industrial processes. So we see that a lot of metal melting industries, they need both carbon, they need low carbon hydrogen, and we see different application of that. And these volumes are already large in millions of tons, and we do foresee that will increase when you see new qualities of carbon coming from methane splitting. As Marilena said, even microwave systems are fairly unknown, but when we speak about carbon coming from methane splitting, 99% of people don't know what it is. So they still confuse it. Do you mean CO2? No, I mean solid carbon. And what do you mean solid carbon? They have no clue. So that's the first challenge. It's about education. And just like the European Union still don't consider. So even if I produce my carbon and my hydrogen in Norway, which with a lower carbon intensity and a lower cost than green hydrogen, the policy document in the EU still don't open the door, because the politicians sitting in the Commission do not know this. It's not about ignorance, they just don't know. So there's a huge opportunity for both of this, the carbon in a lot of industries, the hydrogen in a lot of industry, and a combination of this is, 1 + 1 equals 11. So I'm just waiting for the European Union to open their eyes and saying, guys, why haven't we seen this? Because everything is about green hydrogen, green hydrogen, green hydrogen. And my question is very simple. What if there's something which is better than green hydrogen? Shouldn't we do it? Even, somebody gives this another color. It's all about the numbers, carbon intensity per kilogram. Either it's, coal, carbon, or hydrogen.
Yeah, thank you, Terje, to point this out, this important point. Now I have a question to all panelists. we heard all about high temperature, microwave, and pulse solutions, and what more to split the methane. So could I have some voices in the background? Could you please switch off the microphone? Thank you. Couldn't integrated or hybrid methane splitting hubs combining these technologies be the most effective route forward? Location perhaps could be important, or it could be that we all combine forces. What do you think?
If I can start with that one and saying, first of all, I would say location is key, because it's about access to either biogas or natural gas, and that should be low carbon variants. And Norway, with the vast natural gas resources, is of course a good location. The second part is that Norway, along with Sweden and France, is, when it comes to electricity, it's favorable. So location should be key here. But I do think it's smart to do something together. This is why, seminars like this is valuable, because I'm very sure that the combination of what we are doing, what Storming is doing, and what Titan is doing all together, if we start to combine these elements together, we will get something smarter and better. And I think that's one of the smart move of the European Union with the Horizon program, that you actually go out and you get different programs and you can learn from each other. And these events like this, we can share, we can understand, and we can learn, and we educate. And hopefully that on a commercial level can actually give some purposes. And then from our side, SAID, we are a commercial industrial company. So we are looking to industrialize a number of other EU projects. They can bring the knowledge aboard, they can bring the expertise on board, but maybe they don't have the same drive in terms of you making an industrial, which is what Pierre is looking for, an industrial project, not a science project. Same goes for Christian as well. So I think working together is smart, and using these events, it's a very good way of finding together and saying, let's do something smart together. But location is important, as you mentioned, Michael.
Mm-hmm.
Sorry to interrupt. Just a quick look to the poll. Yes, our participants expect industrial deployment is the answer, and I will launch the next one asking which industries can benefit from CO2-free carbon products. So, Marilena, to you.
Yes, I was just going to say, it's a very good point, combining and using, doing something smart about these technologies. I believe, we all are participants in the same European Union call, and at the end of this call, wouldn't probably be a good idea to get together. We all have to reach a TRL 5 at the end of the project, so we have to fill in our reports, etc. But it's a good approach to say what's best from each technology, because I always believe in combining. We have in our technology, we already combine two things. One is the catalytic technology and one is the microwaves, and we apply microwaves as to enhance catalytic. Why not using something different also together? So I totally agree with this approach. It's a good approach to combine the technology. I'm not going to answer, to where the biogas or biomethane is available. I'm not going to answer to that. I'm just going to say, in terms of the European Union project, it will be kind of good to have a final meeting where we need what to combine and how to do it, and what carbon to give to Michelin and what carbon to give to Elkem, and what Michelin can use, in terms of the technology, another electrified technology, and what Elkem can use as well. So because they are end users of the carbon product, so I believe it's a good opportunity for us to exchange and to be honest about our results.
There was a question or a remark from Anton Scholten.
Yes, I'm Anton Scholten from Highgear in the Netherlands, and I'm working also in the storming project. And I agree. I think we all agree that using methane splitting is helping reducing the CO2 emissions. And I wanted to add that all the different methods produce also different qualities of carbon for different applications. So already Pierre showed that you need different qualities for different parts of the tire. We in storming we are looking for producing carbon nanotubes for electrodes of batteries or fuel cell systems or electrolyzers. So I think all these technologies have their different advantages and different added values to carbon using value chains.
Thank you. Are there more remarks from the audience? I see another hand raised. Can't identify who it is. Can you just raise your...
Charlotte Nordhus.
Yeah, she's participant, but I enabled mic and cameras. So if you would like to say something, it's possible now.
Oh, I'm sorry, it was an accident. So no questions.
Okay. So any more input from the panelists before we go to the audience? If there are any remarks from the audience, especially also in terms of existing EU subsidy deals or industrial funds into methane splitting or carbon valorization. What should be done about it? Is it good enough that the EU has included methane splitting in the Critical Raw Materials Act, which is an important development, but could we light another perspective on that? What are the strategic drivers behind this decision? What could be the reason for that? And how does methane splitting specifically address the EU's goals for resource security and industrial resilience? Has anyone got remarks along those lines?
A quick comment there. Maximilian was with us earlier representing Hydrogen Europe. And I also had a chat with Jorge, the CEO of Hydrogen Europe the other day. And it's very clear that Hydrogen Europe is very, agnostic and open to do this, or trying to, say, we need to have somebody driving this this hydrogen if we are going to use it. If everything needs to wait on green hydrogen or electrolyzers, it's going to take a time. So we need to be agnostic when, if we have sources to make something better than green hydrogen, but the policy document is stopping us today, then somebody needs to check their science books in Brussels. And I think that's very, very important. And I think Hydrogen Europe is one of the players that can actually help the methane splitting industry, whatever version of methane splitting, to get the attention from Brussels to understand that this technology shift or green transition needs to include methane splitting as a part of it. And I think that the opening from the Critical Raw Materials Act is kind of like, the first time the door has been opened to the union. So now I think they will actually see some tractions on this and then saying methane splitting needs to be evaluated at the same level as green hydrogen, and it should be measured upon the same, which is carbon intensity per kilogram of hydrogen.
I see another hand raised, but I can't identify who it is.
Augustine, mic is enabled. In the meantime, a quick look to the poll. Our participants expect that steel and construction would benefit most, and then rubber reinforcement and batteries. I'm watching the next poll in the meantime, and if there are some comments.
So is there any more comments or contributions from the audience?
Okay, this is our last question. What is the most important factor when comparing hydrogen production technologies? So it's open and it is our last one. It looks like everything is important. Yeah, it is changing, and while the poll is open, maybe some last comments from Michael or some of our panelists, and we are almost on time.
Well, just a quick finishing remark from us, so from some side in ColdSpark. Very happy that so many used their time to join us. I would like to recommend and you know all the partners we have coming in, and Michael doing this moderation, and people coming in from Hydrogen Europe and Michelin and Elkem, and of course our partner project Storming and Python. So very valuable that you joined this event, and I hope this was educational for a lot of people. And if you have any questions, at least for ColdSpark and what we are doing, please reach out. You will find the contact detail of me or my colleague Amir. So please do that. But thank you for joining for our part. And I think this was a very valuable event. So thank you very much.
Thank you.
Thank you, everyone, also. And again, just want to emphasize that I wish this technology and this industry to develop so that we can produce some good reinforcing carbon black grades. Thanks.
So from Elkem side, thank you for letting us participate. I think maybe if we want to supply enough hydrogen for the European Union, the amount they need, might be hard only doing it from bio. So natural gas route might be important, at least in the short term. And I think also this would allow, like the carbon market is quite large when you look at metallurgical purposes and so on. So I don't think if you only produce the specialty carbon blacks, you won't reach the hydrogen demand maybe in Europe. So that's where maybe this natural gas route could help. But then we might need to look at how we handle the CO2 after the process, for instance, with CCS. Yeah.
Thank you, Christian. Our Storming and Titan partners, if you would like to say some last words.
Well, yes, thank you very much for doing this. It was quite nice to know where everybody is in the same European call, and to see the end users here, like Elkem and Michelin, to see, that the carbon that we produce can be valorized. It will be, once again, it will be very good to keep in touch and to exchange a little bit more often, and to see when our, the advantages of each technology and the way that we can get together to obtain both the hydrogen and the carbon required by the industry.
Okay, I will add something, then maybe Anton can continue. So I want also to thank because of for the webinar, quite interesting. So I think that at the end, one of the conclusion is that okay, we are doing methane pyrolysis all with electrified reactors. So this is then the main point. We are changing, and the hydrogen and the carbon market is very broad. So depending also on the carbon properties, we will have a different price of hydrogen. And at the end, what we have to do is to decarbonize the hydrogen production and the carbon production. So the single technologies or also the combination of them can be very valuable to achieve this with methane splitting. Okay, I don't know, Anthony, if you can show you. So say something from the industrial part.
Yeah, well, I totally agree. I would say that the hydrogen price is dictated by the hydrogen market, and we more have to look to the value of the hydrogen plus the carbon product. And there we in storming, it's nice that we have quite high added value to the carbon. So that makes it gives us a good chance to be profitable in a shorter time. So what I'm saying is the value of the carbon plus the hydrogen, that's what we have to look at, not really at the different, not only at the hydrogen.
Thank you. So this is what our audience also saying that the CO2 footprint is important, but also the ability to valorize the co-products, the carbon, actually. So if there are no further comments, I would like to close this session, and thanks to all our presenters and to our audience. It was pretty long, maybe, but we tried to make it informative and useful for all. And this collaboration with the industrial partners is highly, highly valuable. I believe so. Special thanks to Pierre and to Christian for joining us. Also to Maximilian from Hydrogen Europe and to our sister projects. Thank you very much. That's on our side.
Thank you.
Thank you.
Bye-bye.
Thank you.
Bye.
Bye.
Bye-bye. Bye-bye.
Bye.
Bye. Thanks.